Welcome back, everyone. Okay, so today what I want to go ahead and cover is a new type of transistor. This one is known as the field effect transistor, or what everyone's just going to say FET for field effect. Transistor. Okay, now this differs from our bipolar junction transistor, both in construction and features, I guess we can call it. Okay, now when you're looking at a BJT, we know that it's that base current that controls the collector current. Okay, so IB controls IC. That's the important relationship. The current going in controls the current going through the device. However, with a field effect transistor, that's actually going to change for us. Instead of the current being controlled by another current, IB, now what we're going to have is a really cool situation where the current is controlled by a voltage. Let me toss that marker. It's not doing me any favors. Okay, so let's go ahead. Let's draw up a very simple circuit with a FET. Okay, now the symbol that we use for a FET, for a generic field effect transistor, is looks like this. Some of the names are going to change here too. Okay, and so here is our field effect transistor, and I have two voltage sources applied to it. One, well, I need to give some names for these. Okay, so the input is not going to be the base, okay? The BJT had its input called the base. For a field effect transistor, that input is actually referred to as the gate. And we'll just denote that with a G. Okay, and up here is not the collector. Up here is the drain. And down here is not the emitter. This is referred to as the source. Okay, so G, D, and S. Okay, and if we apply a voltage to the drain, then we know that as VDD. And the voltage applied to the gate will be known as VG. VGG. Okay. And the names are just different, you know, just to confuse us, basically. Now, it's actually because of the construction. So the construction of a FET is quite a bit different than the construction of a BJT, exactly how it sits on the silicon when you make it at the semiconductor level. And so it doesn't make sense to have a base, but it does act like a gate, hence they have the gate. And then if you're changing one name, you might as well change them all. So we get gate, drain, and source. Okay, and then the current that goes from the drain to the source, you guessed it, is the drain current. Okay, so ID is the drain current. And the voltage that's at the gate would be known as VG, the gate voltage, and the voltage at the source, V sub S, and the voltage at the drain, V sub D. Okay, so all of that still holds true. Now, here's the deal. The current is always going to flow from the drain to the source. And the current ID is going to be controlled by a voltage V sub G. Now, this actually is going to end up being quite simpler for our analysis use case. In fact, Fets are going to be much simpler for us because of how we use them and what we typically use them for. So now at this point, I think we need to talk about the family of Fets. Fets have a very large family with many different kinds of Fets. And so, as far as this class, we need to focus in on one. And so you have to kind of pick the most commonly used field effect transistor that computer engineers typically encounter. Let's face it, we only have 2 classes to get through this type of analog stuff. I did forget to mention one thing before I get into the family that I just saw. I forgot to mention a very important thing, which is we do, just like we have 2 different types of BJT transistors. I guess that's a little redundant. We have 2 different types of BJTs, NPN and PNP. We also have that same type of relationship when it comes to FETs, except they're going to be called N-channel and P-channel. Now, the N-channel FET looks like that, and the P channel just has the arrow facing the other way. And if we understand one, then understanding the other one is pretty straightforward. And we will spend a little more time looking at the P-channel MOSFET in a later class than we did at looking at the PNP transistor. The PNP variant of the bipolar junction transistor, we did not spend that much time on. We just don't have that much time in class. But in the case of the FET, and specifically the type of FET that we're going to work with, we will definitely go into the P-channel version of it, but let's focus on the N-channel first. Once we understand this, looking at the P-channel is going to be a great deal simpler. Okay, so now we can go ahead and discuss this family of FETs. That is, if I can grab another piece of paper here. Okay. There we go. So under this whole umbrella of field effect transistors, we're going to break it down into 2 fundamental types. One is going to be the JFET. Now, the J stands for junction field effect transistor. I'm not going to bother writing out the whole thing. The junction field effect transistor. I already wrote field effect transistor on the previous slide. Let me stick with acronyms. And we have, again, an N-channel variety and a P-channel variety of the JFET. Now, we're not going to spend any time looking at the JFET. The JFET is very, very high impedance on its input. It's very good for high amplification of very, very tiny signals. However, I think what's going to be more useful, actually what I know is going to be much more useful for us, is to look at another type of field effect transistor. That is known as the Mosfet. Now this one, I'm going to write out the whole thing in all of its glory because you got to give credit where credit is due. Metal oxide semiconductor field effect transistor. And believe me, every single one of these words actually means something. Metal oxide refers to its fabrication, the semiconductor, because it's made with a semiconductor. It's silicon. Field effect transistor, because it is a transistor that is switched by manipulating the electric field inside the device. Okay. And now, under this category of MOSFET, it actually breaks down into two others. One is the depletion mode. Or I should say depletion type. The D MOSFET. And with that, of course, we're always going to have these two versions, the N channel and the P channel. And the enhancement type is the other one. Let me move my face out of the way here. Okay. E MOSFET, which is the enhancement type. Now, under this category, of course, we also have our N channel and our P channel. And the enhancement type of MOSFET is, generally speaking, what we use a lot of in computer engineering. In fact, I'd say we tend to use these enhancement type MOSFETs a lot more than we do even like BJTs, which are kind of the general purpose go-to transistor you usually try to solve using first. These MOSFETs have some really incredible features about them that is going to allow us to do a lot of things that you really couldn't do otherwise. And we will be seeing that over this class, the next class, and probably I think we'll be spending 3 lectures on MOSFETs. Okay, so what are we going to be focusing on? Well, we're going to only spend our time talking about the enhancement type MOSFET, which we will actually just be calling MOSFET. In general engineering vernacular, people just say MOSFETs. People don't really make that distinction unless they're using a depletion mode, and then they may say like, oh, it's a D-type MOSFET. But generally speaking, and we will be sticking with the N-channel variety just for starters. Okay, so let's go ahead. Let's zoom in on this MOSFET. Now, the way these guys are constructed, if you look at taking a chunk of silicon, a chunk of semiconductor material, not a good conductor, not a bad conductor, it's a semiconductor. We have a substrate. This is your silicon. This is what you start off with. And then as you construct this MOSFET, you add impurities to it. You dope it. You create areas that are more conductive either as a P-type material or as an N-type material. So what happens first is this gets doped with a strong, well, not with a strong, but with a P-type material. So you're adding an impurity that's going to make it more positive, and you make something more positive by adding something that has less valence electrons. So you'd be adding something that's got a group 13 or 3 valence electrons. And then once you have an area that is doped more P, then you go ahead and add these 2 areas on the sides. Which are doped as N. And to make an N-type material, you add an impurity that has an excess of electrons. So you add something from that group 15 from the periodic table of elements. And you get an extra electron for every dopant atom that you add in there. So we have an N region, we have an N region, and we have a P-type region. And now we get to talking about how we construct the gate. Now the gate is actually constructed by growing this oxide. Okay, and that's actually where it gets its name from. Metal oxide insulation. Now, you think of metal as being conductive. However, when you grow this layer of silicon oxide on top of here, it is actually an insulator. It will not conduct. And so you now create a conductive material on top of this. And that is where you get the gate. Okay, so what you have over here is a conductive material right in the middle of these 2 N-type regions. Now, if we go ahead and add some connectors, some conductors over here, so you can connect or tap into this N-type material and this N-type material. You get your drain. Okay, so let me go ahead and let me use a different color so we don't get confused and think we're actually referring to this. Let's just call this the drain. Okay, and similarly, if we do that to the other side, we're going to get the source. Okay, so we have our gate. We have our drain, and we have our source. Okay, now there is one other connection that is often left out in most drawings. There is actually a connection from the N-type material over here on the source down to the body. And I only show this for completeness, but we don't really have to pay too much attention to it. Now, when you construct your MOSFET like this, let's go ahead and make a comparison to the schematic symbol. Now, as well as the formal schematic symbol, we also have an abbreviation, which is very convenient when you start drawing lots of these. Okay, and yeah, we have the schematic symbol and the abbreviation for the schematic symbol. Okay, and you can use these interchangeably. However, there's a little more information that's generally shown with the formal schematic symbol. Let's go ahead and let's make this is a an N-channel enhancement type MOSFET. Let's go ahead, let's make a P-channel MOSFET. It's almost the same thing, except you're going to have an N-type substrate, 2 P, and we call these wells. And you still have that metal oxide insulation. That's kind of the defining feature of a MOSFET. We still have a gate. We have some taps on the side. And the schematic symbol for a P channel changes just slightly. Drain, source, and gate. The names still apply. And the abbreviation ends up being the same as before, except we have a little inverter bubble over here. And this will make a lot of sense probably next class when we show the P channel variety. And I think yeah, I kind of like the MOSFET topic because it's a little eye-opening once we see how you can use these MOSFETs in order to construct all the digital logic that we use. All of our digital logic, our FPGAs, our microcontrollers, all of that stuff that you learn in 201, 301, 440, etc. All of that stuff is made fundamentally of these two varieties of MOSFETs. And so an AND gate, a NOT gate, an XOR gate, a NOR and NAND, they're all constructed with several of these MOSFETs internally, and we do some incredible things with them. So this is the construction. Let's talk about the MOSFET action. Why is it that the voltage controls the drain current? So if we go ahead and let's draw physically what this MOSFET looks like. P, N, and N. we have a VGG. And in this case, what we care about is the voltage between the gate and the source. Now, the voltage on the gate is just this side of this voltage source, and the other side of that voltage source, VGG, is just tied to S. So the voltage between the gate and the source we would express as V subscript GS. So this is voltage between gate and source. And if we have 0 volts here, well, what ends up happening? So let's go ahead and establish kind of a few things here. We have free electrons over here, free E's, and we have free electrons over here in the N region over here. And so the idea is that we want to be able to push the current through this device. We would call that ID, the current going from the drain to the source. However, with no voltage applied to this gate, it can't do that because this p-type material doesn't have free electrons to allow the electrons to actually start pushing through here. So ID ends up being equal to 0 amps. In other words, this acts like an open switch, not allowing any current to flow through. Now, if we go ahead and draw this same thing, but bump up the voltage that's being applied to the gate, something interesting is going to start happening. Okay, if we increase VGS, and we're actually going to have a number associated with this. That number is referred to as VGSTH. This is known as the threshold gate source voltage. Let me write that down. Okay, so the gate source threshold voltage is the value that we must exceed. The value that VGS, the voltage between the gate and the source, must exceed or must be greater than this threshold gate source voltage in order to get the drain current to flow. Now, VGS-TH is a number that you would get from the data sheet. So if I open up a data sheet, you're going to find out that VGS-TH is equal to some value. So let's just, for instance, let's just say that VGS-TH is equal to 2 volts. And let's say that our gate source voltage, let's say this voltage source is set to 5 volts. Well, if it is greater than VGS-TH, something is going to start happening. Well, what is it that starts happening? Well, we are placing a positive voltage on this conductor right here. However, notice this is an insulator. This metal oxide is not going to allow any current to flow into the device or out of the device, right? Because it's an insulator. But wait, I have a conductor on the left side. Oh, but wait, I also have a semiconductor on the other side. So I have a conductor and I have a conductor, and I have them separated by an insulator. Look what I got. I got a capacitor. All right. I have a device that can store charge. And so what ends up happening is when I place positive charge on this side, I start to get electrons building up on this side. There are some electrons floating around here. And by me placing positive charge over here, I have to get negative charge over here. This is the same thing that happens when you charge up a cap. If I were to do this, I will reach a point where I have built up a bunch of positive charge on this side and a bunch of negative charge on this side. And now this guy is storing charge. He's got energy stored in him in the form of electrons and lack of electrons. So the same thing is happening here. By me applying a voltage to this gate, I am developing positive charge on one side, and similarly, I'm getting negative charge on the other side. This is known as the inversion layer. Now that I did pull some electrons over here, I just created a bridge. I just created a bridge for the electrons from this N region to actually push their way through to the other N region. I have created a channel. A channel as in a moat, as in the English channel. I just created a path for my electrons to actually move through. And it is called the inversion layer. So in this case, I absolutely will get an ID greater than 0 amps in this case, because I have applied a voltage to the gate that is sufficiently large enough, in other words, greater than my threshold voltage. What did I said, just for example and illustration purposes, we could just say it's 2 volts right now, and 5 volts is sufficiently greater than 2 volts, and so we do get this inversion layer, and therefore we do get charge going through. But notice, once the charge has developed upon this capacitor that's been formed here, I do not get any more current flow, right? Once your capacitor is charged at time 0, yes, you get current flowing through the cap. But once the voltage here matches the voltage here, so once VC let's call this VS and let's call this VC. Once VS equals VC, no more current flows. In other words, IC equals 0. And that's the same thing that's happening here. So it is merely a voltage being applied to the gate that causes this inversion layer to develop, that creates the channel for the drain current for these electrons. Now this is, I'm showing conventional current. Yeah, the conventional current's going down. Yes, I know the electrons are actually moving upward, but whatever. Conventional current's going down. That's all I care about. So I am getting a flow of current through this device. In other words, it is behaving like a closed switch. Okay. Now, great. So I have a voltage-controlled switch. Now, I think the easiest way to look at a MOSFET is to think about it as a resistance that is controlled by the voltage on the gate. That's just the easiest way to look at these things. And in fact, it's not a bad way to look at it, because the data sheet that you would use for a component when you purchase it from a manufacturer will actually give you resistance values for the MOSFET that you're using. And they'll give you a graph of those resistances. So this model is totally valid and accurate. It's a voltage-controlled resistor. Okay, so how would you generally hook up something like this? Well, generally speaking, you would use an N-channel MOSFET many times like this, where what I want to do is control the current going through a load, whether that load is a motor, whether that load is a whatever it is, whatever you want to turn on and off. You would put the device, put that load up here, and then use the MOSFET to either behave like a open switch or a closed switch. I know I said those opposite as I wrote them. Closed switch over here and open switch over here, depending on the voltage applied to the gate. And this would be known as VGS. Now, we're going to need some parameters. Now, we already talked about the gate source threshold voltage. That's the voltage that VGS must exceed to get this to behave like a closed switch. And a closed switch is very similar to a resistor of 0 ohms. And a open resistor looks very much like a resistor with infinite ohms. Okay. And there are varying degrees of closedness. You can think of this as the saturation mode the saturation mode of a BJT, except that the saturation of a MOSFET is much better than the saturation of a BJT. When a BJT is in its saturation mode, you typically take that saturation voltage to be like 0.2 volts. But as I will show you, the saturation, quote unquote, saturation voltage of the MOSFET, in other words, what's the voltage drop between the drain and the source of the MOSFET when it is fully closed, we're talking like damn near 0 volts, which is awesome for our applications and awesome for our intended usage, because now we have a transistor that truly looks like a closed switch. So when I say this acts like a variable resistor, depending on the voltage that's applied to the input, where do I get that value from? So we have another value as well as the gate source threshold voltage, or VGS, in parentheses, TH for threshold. We also have a value called RDS on. This is the resistance from drain to source when the MOSFET is on, saturated, closed, however you want to talk about this condition. This is the condition when our MOSFET is behaving like a 0 ohm resistor, like a closed switch. This is what the data sheet will tell you. They'll specify an RDS on value. Okay, now I can go ahead and tell you right now, it's not exactly 0 ohms, but it's damn close to it. We're talking 0.1 ohms. Depending on how good of a MOSFET that you get. Now, ideally, I'd like this to be as close to 0 as possible. You're never going to get absolute 0 ohms, but you can get very close. You can get in the milliohm range. And so the type of MOSFET that you use will tell you in the data sheet what the resistance looks like when you have exceeded that gate source threshold voltage. Okay, so let's go ahead and let's set up an example with a real MOSFET, and let's go ahead and see how we can use this. Okay, so I'm considering V in to be the voltage input to this, and a voltage always is between 2 points. So I'm saying that the voltage on in is between this and 0 volts and ground. I'm just kind of trying to explicitly say that by drawing this other terminal down here, so that V in, so there's no confusion that V in is between this point and this point. Let's see. We will call that V in. Now, we need to go ahead and put some labels around here. We will have a gate. We will have a source. We will have a drain. We are going to have a drain current. And we also need a real MOSFET. I need to give you some real values. So I'm going to go ahead and pick an IRL, an in real life Z24. It does not stand for in real life. I believe it stands for international. What does IRL stand for? I got to Google this. It's an international rectifier. It was purchased by Vishay. Let's see. Yeah, they don't have the original. I believe it's International Rectifier, and what ended up happening was Vishay purchased them out. They kept the part number because you don't want to change the part number on 60, 70-year-old engineers. You want to keep the same part numbers, and then you make a new data sheet and you just put your logo on it, and then that name just sticks there forever. Okay. So, an IRL Z24. Now, what's the deal with this guy? Okay, so we need to have a gate source threshold voltage. That's the first number that we're concerned with. We want to know at what point does applying a voltage greater than that actually cause this to behave like a closed switch. Now, I'm saying typically it's 1 volt, and that's what the data sheet says. Typically it's 1 volt, but it also specifies worst case 2 volts. So it could be 2 volts, let me say max. So in the worst case, it could be 2 volts. But typically, under most situations, it acts like 1 volt. Now, what does that mean, worst case? Well, worst case, ideally any voltage here would cause this to be on, but it doesn't work that way. We have to exceed some certain voltage, and having a 1 volt threshold voltage is actually pretty good, because it means that anything that is, 3.3 volts, 5 volts, our typical digital logic levels that we generally work with are sufficient enough to turn this MOSFET / switch to turn it on, to allow the current to flow through. What's worse than 2 volts would be 3 volts, 4 volts, 5 volts, because it becomes harder and harder to actually turn this on. So that's what I mean when I say worst case, okay? But under most operating conditions, you can expect 1 volt. But if I saw this in the datasheet, I would design and make sure that I'm always above 2 volts whenever I need this guy to be on. Okay, so that's VGSTH. We also are going to need an RDS on value. Okay, now the RDS on is what resistance does this MOSFET behave like when our applied voltage is larger than 1 volts. So when we've exceeded the gate source threshold voltage, this MOSFET will behave like this RDS on value. Okay, now this was taken straight from the data sheet. It says RDS on equals 0.1 ohm when VGS is equal to 5 volts. So it looks like when we are about 4 volts greater than our threshold voltage, you can expect this MOSFET, it is guaranteed to be behaving like a 0.1 ohm resistance. Now 0.1 ohms might as well be a closed switch in my opinion. 0 ohms would be a perfectly closed switch, but 0.1 ohms is damn near close enough. You wouldn't even find a 0.1 ohm resistor in your resistance kit. This is generally 0.1 ohms it might as well be a wire at that point. It is a very low amount of resistance. But the manufacturers know that you are interested in more than just this. You may also want to know what is RDS on when VGS is equal to 4 volts. So they've given that to us as well. Okay, so looks like when we're not quite at 5 volts, if we're at 4 volts, we get it to act like a 0.14 ohm resistor. Okay, again, tomato, tomato. This might as well be a closed switch. So perfectly great that we have a low resistance when we have a gate source voltage of 4 volts developed between the gate and the source. Okay, so the voltage between these two. Okay, so armed with this information, we know what the value of the load is, and we know what our, well, I'm going to change my input. Let's just say that my input comes from a microcontroller. Maybe it's an 8051, and maybe it's 5 volts when the output pin is high, and maybe it's 0 volts when the output pin is low. Let's keep this simple and just look at it from the perspective of 5 volt logic coming from one of our microcontrollers. Okay, so now we do have to analyze this twice because we have two different conditions when our microcontroller is driving this at 0 volts and when it's driving it at 5 volts, okay, depending on whether we wrote a 1 to that pin of the microcontroller or if we wrote a 0 to the pin of the microcontroller. So let's just say we want our microcontroller to control this motor using this MOSFET. This is a very typical, very common usage of a MOSFET. In fact, I would say 98% of the MOSFETs that you would ever use in your life are probably going to be this type of use case where you're operating them as a switch. So that's why I'm teaching it this way. Okay, so let's go ahead and let's set up two different columns here so we can calculate this guy twice. Okay, we're going to look at this circuit under two different conditions. When it is off, this means Vin is going to be equal to 0 volts. And we're also going to be looking at it when it is on, when Vin is equal to 5 volts. Okay, now this, I promise you, is so much easier than our BJT, any of our BJT analysis, because all you have to look at is just the voltage and what that voltage is with respect to VGS-TH. Once you know that, you can figure out everything about this circuit. So let's look at the off case. VGS equals Vin, which equals 0 volts. Hopefully we all agree on that, right? The voltage between the gate and the source, given that Vin is applied to the gate with reference to the source, if this is 0 volts, we have 0 volts applied to the gate source. So we get 0 volts there, okay? VGS is less than VGS-TH. since the typical VGS value is 1 volt, and I know that 0 volts is less than 1 volt, so we know that our MOSFET is actually in cutoff. Since our FET is in cutoff, we would expect this is behaving like an open switch, therefore ID is equal to 0 amps as I've said here. Okay, so what is the voltage between the drain and the source? Well, if this is an open switch and we have 0 current flowing through this, I get 0 volt drop across my motor, but I still have the potential to do work, so I measured 12 volts between the drain and the source. And we should also be interested in our VRL, or the voltage across our load, which we know if we have 0 current going through it, it should be 0. And all I did was expand out Ohm's law over here, saying that the voltage drop across the load is equal to the current flowing through the load times the resistance of said load. Okay, so we have 0 volts. This is everything we need to know about this circuit for the case when we're applying 0 volts to it. Now, let's go ahead, let's do something a little more interesting. Let's actually turn this guy on. Okay, now what's VGS equal to? Well, if I apply 5 volts over here and this is 0 volts, then I have 5 volts. So VGS equals 5 volts. But let me go ahead and let me expand this a little bit. VGS is actually equal to VG minus VS. Now I know why this was looking funny to me. I wanted to use an uppercase. Now I'm writing this in order to expose a very subtle issue with using MOSFETs, which is the voltage on the gate is not necessarily the voltage between the gate and the source. I'll say that once more. The voltage on the gate is not necessarily the voltage between the gate and the source, because it depends on what this side of the MOSFET is connected to. Since this side of the MOSFET is connected to ground, and this we are taking as 0 volts, then what you're actually saying is the voltage at the gate is equal to 5 volts, and 5 volts minus 0 volts equals 5 volts. It's a very subtle distinction, but I see problems with using MOSFETs all the time where the MOSFET is not actually the source is not connected to ground. Now, that problem comes because the application is so simple. People often overgeneralize a MOSFET and say, oh, it's just a switch, and if it's just a switch, then I can put it up here. If I put my MOSFET above the motor and put my motor below the MOSFET, then notice that my source is no longer attached to ground. It's no longer being referenced to 0, so the voltage on the gate is not the same as the voltage between the gate and the source. Okay, I'll do an example of that later if you're a little confused by what I just said with the MOSFET being above the motor and the motor being below. Just know that an N-channel MOSFET, for right now, an N-channel MOSFET must be below the load that you intend to put current through, specifically because we want the source connected to ground. Okay, so let's go ahead. Let's look at this. So we end up getting 5 volts minus 0 volts, which equals 5 volts. Cool. So is VGS greater than VGS-TH? Absolutely. Yeah. VGS is much greater than VGS-TH. And if that's the case, then we know this first line holds true. We know that this MOSFET's going to be behaving from the perspective of the drain and the source, the resistance between the drain and the source. It's right here in the name, right? RDS, resistance between the drain and the source. When the MOSFET is on, which it is because we've exceeded that gate source threshold voltage, so it should be behaving like a 0.1 ohm resistance. So armed with that information, you can now calculate what ID is equal to. ID is going to be equal to VCC divided by both of these resistances because they're both in series. So I have 10 ohms plus my RDS on value, which is 0.1 ohms. And so RDS being 0.1, RL being 10, we get 12 volts divided by the series combination of both these resistances. And so now we know what the drain current is. So very easy to figure that out. Now let's go ahead and let's figure out what the voltage is between the drain and the source. The voltage between the drain and the source is just going to be equal to, well, the current flowing through the drain and the source multiplied by the resistance between the drain and the source. Since this is acting like 0.1 ohms, this might as well be a 0.1 ohm resistor, and I have ID flowing through it, so just apply Ohm's law. So VDS is going to be equal to ID times RDS on, which ends up being equal to 1.188 times 0.1, which equals 0.119 volts. Okay, so you can already see we actually have a pretty small voltage drop across the MOSFET. That is good. Ideally, I'd love for there to be 0 volts across it, but I'm never going to get that. But what I can do is I can hope for a very small value. And 0.1 volts, actually, I will say 0.1 volts is actually a little high. I typically, when I use these, I get much lower. I can get them down to like 0.01 or even lower than that because I'm speccing out better MOSFETs. This IRL Z24 is one that I picked from the book that they used in an example. And the IRL Z is not that great of a MOSFET, but you can get much lower than this, like 0.01, for not much more cost of an IRL Z24. Okay, So let's go ahead and finish calculating all this stuff. That's VDS. Let's figure out the voltage across the load, which equals ID times RL. Okay, just Ohm's law there. I'm just going to give you what that value is. It's 1.188 times 0.1. So you're going to get, no, sorry, I'm way off. 1.188 amps times 10 ohms. Just apply Ohm's law. You get 11.88 volts. This is good. I want most of my voltage to be dropped across my motor. The less of a voltage drop that I get across my MOSFET means the less power my MOSFET has to dissipate. That's less power that's wasted. That's less heat sinking that I need in order for my MOSFET to safely control large currents. So the lower I can get that voltage drop, the more current I can put through my MOSFET without the MOSFET dissipating as much heat. And when you're using MOSFETs, heat is the name of the game with them. That's where we get into trouble with using MOSFETs, where they get really hot and they burn up because you're putting too much current through it. Well, people will say you're putting too much current through it. No, you should be able to put a lot of current through it. It's just you have too high of a voltage drop across it. And so the two of those multiplied together gives you your power dissipated by it. So let's go ahead, let's look at the power dissipated by the load versus the power dissipated by the FET. Because as I said, the power is what we really care about when it comes to using these MOSFETs as a switch. They tend to work as long as we don't burn them up. PL, or the power dissipated by the load, is going to be equal to the voltage drop across the load times ID, right? P is just equal to IV. So what you get is 11.88 volts times 1.188 amps, which equals 14.1 watts. Okay, now what we've all been waiting for is the power dissipated by this MOSFET, or power dissipated by the FET. Okay, it is a field effect transistor, so we can go ahead and abbreviate it and just call it a FET. That's going to be equal to V sub ds, the voltage drop across the MOSFET, times the current going through it, right? P is just equal to IV. So if VDS is my voltage drop across, multiply that by ID, I get my power. So we get 0.119 volts, which is the voltage drop across the FET. We calculated that earlier. And that gets multiplied by the current going through it, which is 1.188 amps. And we get 141 milliwatts. It's a thing of beauty, okay? So while our load is dissipating 14.1 watts of power, my switch, quote unquote, is only dissipating 141 milliwatts. Okay, so this is where the power of these MOSFETs come from, which is that they have very low on resistances. And those very low on resistances allow us to put large amounts of current, 1 amp flowing through this, while only dissipating a very small amount of power from them. Okay, and power is what causes the problem. Because the more power you dissipate from it, the more your transistor is going to burn up and catch fire. Now, in the case of a BJT, good luck. Good luck doing this with a BJT, because a BJT is going to develop a much higher voltage drop between the, I got to switch my terminology now, between the collector and the emitter. And that larger voltage drop means if I put 1 amp through there, it's going to be catching fire really quick. Okay. Maybe I'll have to set that up in a future example and blow up one of my 1,000 3N04s for the sake of just blowing up a transistor for fun. Okay. So that is everything that I want to cover for this introduction to MOSFETs. They are fairly simple devices once you're comfortable. I think the hardest part is getting used to the terminology of VGS, TH, RDS on. You know, just remember these. Look at the subscripts. I know I used to be super confused by this stuff because you'd see subscripts and like you'd see like sentences written out below these letters. Just read them and take them for what they are. If there's a V and there's a G and an S, it's the voltage between these 2 points. And then this TH is just the threshold voltage, some arbitrary number decided by the manufacturer that we must exceed. Same thing over here. The resistance between the drain and the source when the transistor is on. Okay. Don't get overly confused by the terminology, by the what's that called? By these variable names. Okay. And rely on your basic rules, because your basic rules always end up being correct. I have yet to see an instance where KVL and Ohm's law, where those aren't applicable, where those aren't true. That just doesn't happen. So with that being said, have fun. Take care. Bye-bye.